I'm Anton, and this is the Climatologist Abroad. This week I'm in Svalbard, a remote island in the Arctic Circle, where in winter the sun doesn't rise for months. The cold is sharp, the landscape is barren, but still a small community thrives on the island, one whose warmth stands in contrast to the environment. Svalbard is at the forefront of the effects of climate change, warming nearly 4 times faster than the global average, and recently its coal power plant, the last in Norway, was permanently shut down. This is a stark reminder that even in the most remote corners of the world, the energy transition is already underway. But transition to what exactly? When Svalbard shut down its coal-fired power plant this year, it switched to diesel. Renewable sources aren't available because the wind doesn't blow and the sun doesn't shine for a good period of the year. What are the options in this case? Today, I want to chat about nuclear, the energy that divides opinion like almost no other in the climate debate. Chernobyl, Fukushima, 3 Mile Island. These names are burned into public memory, fueling fears about safety and risk. Yet at the same time, nuclear provides nearly half of the world's clean electricity. It's a constant to and fro, where countries like France rely on it for about 70% of their power, while Germany shut down its last reactors in 2023. But what about the innovations occurring in the nuclear space? My guest this week is Janne Wallenius, the founder of Blykalla, a startup and research facility that has been developing what's called Small Modular Reactors, or an SMR for short. Unlike the massive, expensive nuclear power plants of the past, SMRs are designed to be built in factories and deployed quickly. They promise lower costs, safer designs, and greater flexibility, potentially making nuclear viable in places where it hasn't been before. Some see them as a game changer. Others aren't convinced they can scale in time to matter. So where does that leave us? Now, I'm not here to be pro or anti-nuclear, but in the business of climate change, this is an essential conversation to have. Because if we're serious about cutting emissions, we can't afford to ignore any option. Let's get into it.
So we're here in Svalbard, in Longyearbyen, in total darkness. I've had a few days to sit in the darkness and face my demons. Why are you here? You know, I understand from your part that you've got a cabin. You come here regularly. What does this place mean to you?
I'm just totally in love with the Arctic nature and the let's say post-industrial surrounding that we have here on Svalbard, with the old mining industry still being present in terms of its remnants, and the combination with the barren nature is what basically makes me come here.
It's beautiful, isn't it?
Yeah.
And sleep is helpful too in the total winter.
Yes.
So let's start with what's happening now with Blykalla. So you had a lot of recent big milestones this year, and they've caught attention in Europe and worldwide, and our audience is eager to hear what's next. So first of all, tell us about Blykalla. If you had 1 minute to explain what the company does to someone new to the space, what would you say?
What we are doing is that we are industrializing an innovative technology for producing nuclear power, which is based on using liquid lead as a coolant to transport the heat out of the nuclear chain reaction. And this is, as many things in nuclear, technology that has been used historically, but it was not yet commercialized, and the latter is our mission.
I'm really keen to drill into that, but let's shift back to your journey and how you kind of got into this space in the first place. So where did it all begin? You know, what was growing up like, and what was the key moment that made you decide to go down this path?
In Sweden, we had a referendum to phase out nuclear power following the 3 Mile Island accident. So Sweden actually voted to phase out nuclear power by 2010. And I thought at that time, I was 12 years old when this referendum happened, that, why should we try to vote away for a problem where we actually can address the technological issues that people might have with nuclear power, such as the nuclear waste problem, such as the safety problem.
So let's talk about that. So you did your postdoc, and you became a professor of reactor physics at 28, which is extraordinary in itself. You've been a professor for nearly 30 years. How has that shaped, do you think, the way that you communicate about science? And why is that important in the context of your role now?
Right. Well, I was given the opportunity to start working in a field which at that time was considered to be highly undesirable. Sweden was going to phase out nuclear. There was a law in Sweden stating that anyone attempting to make drawings for a new nuclear power plant to be within Sweden would be punished by 4 years in prison.
Wow. Okay.
So let's say it was not very opportunistic at that time to start working on the topic. But that was just another driving force for me because, I'm going to show the world that this is going to.
Don't tell me I can't do it.
Nobody was ever put into prison because of the law, but it meant that the government did not fund research on nuclear power. So we had to find funding from other sources, from the European Union, from the nuclear power industry. But me and my colleagues, we were actually successful in acquiring funding and to start actually building out this knowledge on advanced nuclear power that had been lost in Sweden. There was not a single PhD thesis in reactor physics at Engage for 17 years.
Wow.
So basically the research area had been destroyed. But we were able to actually recover and build up competence through participation in international projects, in particular, and Davos. And step by step, we were able to grow. And finally, the law was abolished in 2008, I think. And then I was able to get the first new grant to develop.
And bringing the public on the journey with this, what were the 1, 2, or 3 key messages that you found started to resonate most effectively?
And the first thing that was that we were showing that it is technically possible to actually recycle nuclear waste to reduce the time you need to store it, insulated from the biosphère from 100,000 years to less than 1,000 years. And so that was, a breakthrough that made it possible to create reports, positive reports with the public. And in doing so, we were also studying this lead cooling technology that also helps to make a nuclear power plant safe for at a lower footprint and at a lower cost. Modern nuclear power plants are in general safe. I wouldn't say that the competing technologies are less safe than a lead cooled reactor. That we can create we can make a reactor that is both safe and cheap in a very compact form. And those things are related because smaller reactors in general are safer because they contain less radioactive elements. And the small reactors are also in general quicker to build. And therefore, they will be also cheaper.
Got it. It's very clear, is it? So your recent deal to advance Blykalla's technology has been big news. What's the story behind this milestone, and why is it significant for the broader nuclear field?
So the agreement that we signed with ABB is an important milestone for us because ABB was the company that built the Swedish nuclear power stations in the 70s and the 80s, and then they went out of nuclear because they didn't see an immediate future for it, and therefore it's a major breakthrough that they're coming back to nuclear together with Blykalla, and that is very important for us. So together with them, we will build the next generation of nuclear power in Sweden and elsewhere.
Congratulations. It must have been a lot of hard work to get to this point.
Oh yeah, and the company's been around for 11 years now, but now it's really taking off.
You mentioned cooling. We talked about lead. What's the single biggest problem your reactor solve, and why is it essential for the energy transition?
Yeah, well, liquid lead has been used as a coolant for atomic submarine reactors in the 70s and the 80s in the Soviet Union. Now that experience showed that you can build very compact power power reactors and operate them reliably eventually. Now, with the materials that the Russians had available, they were only able to operate these reactors for at most a year at full power, which in a submarine means maybe 10 years at 10% average power. So what had to be invented in order to make this technology useful for commercial power production is that you had to develop steels that were corrosion tolerant to liquid lead. Because liquid lead is highly aggressive to conventional stainless steel, which do not have a lifetime longer than a year in this environment at the operating temperature. So what we set out to do at the release is the technology, me and my colleagues in 2009, which is now almost 16 years ago, is that we tried to develop an alternative solution which is based on the use of aluminum alloyed steels. And when you add a few percent of aluminum into your steel and it's in contact with a liquid lead that contains some oxygen, it will form an aluminum oxide on the surface of the steel. And that aluminum oxide turns out to be magically corrosion tolerant.
Wow. So you were doing your PhD in fusion. Your company works in fission. What happened?
Well, after having worked 4 years on this type of fusion, I realized, this is not going to work. Because fusion needs a fuel that doesn't exist on the planet. So if in a fusion reactor, you need to make your fuel continuously, the tritium fuel. And I realized that this was going to be not just only difficult, but from an industrial perspective, more or less impossible.
So doing some of the research and the background to this, as I understand it, tritium is a type of hydrogen. We only have 25 kilos of it globally today. We're using it up. We need it to start a reaction in the fusion context. And there's some theory that used in fusion reactors, we can make more of it.
Yes.
But that's not proven.
It's not proven. And the accomplishment of actually producing enough tritium in the fusion reactor must be achieved during the very first week of operating the first fusion reactor.
Otherwise we run out.
Otherwise we are out of tritium. And then that seems like a bigger challenge than we can actually meet. So having realized that I need to work with something that actually solves the nuclear power issues, and I'm therefore starting as a postdoc at the Royal Institute of Technology in Stockholm, working with nuclear waste recycling or nuclear waste transmutation. And this was in 1997.
So that's a good point to pivot to the science and the innovation behind what you're doing. So we've talked about lead-cooled reactors. What makes them, unique compared to other innovations that are happening in the space? So sodium-based reactors, or some of the large reactors that people are innovating with. Why lead-cooled specifically?
Lead is a very benign cooler to work with because the chemical reactions are quite slow, like corrosion. And then of course, the safety aspects, so the safety aspects means that you can make a reactor that's what we call passively safe in a very compact format. And that leads to the opportunity of making these reactors more quickly, to build them more country in an automated factory. For instance, the vessel that you keep the lead in, a little bit counterintuitively, it needs to be much thinner than the vessel that you need for hosting liquid water or boiling water or other coolants. So this means that you can fabricate the reactor vessel in less than a month, well, as compared to 3 years, which it takes for a water-cooled reactor.
So when you say a year, you're saying, so once you get your factory going, we'll plug it into this in a second, but let's drill in. it'll take you a year in this factory to generate one new reactor
unit, and then it will take another year to install it on the site and go to criticality and commission it until you are in full power production. So we aim at that 24-month cycle from placing an order to having the reactor producing power.
See if that's insane compared to some of the timelines that we've been talking about. Let's think about the technology. So this isn't entirely novel. We talked about Russia developing this for their submarines. How long ago was that? How has the technology shifted since they deployed them into their submarines?
Yes. So what they were able to do with the submarines was that they were able to control nuke on it. So they could achieve a 1-year lifetime of the submarine reactor at full power. And then because the submarine only operates at full power rarely, that meant 10-year calendar time left.
So it corrodes, but it corrodes over that 10-year cycle.
Yeah, exactly. Now, for a commercial reactor, that is not acceptable. We need to operate 24/7 for 90% of the time over a minimum of 25 years, preferably 60 years. So you need to develop a new steel then. And the Russians took the path of developing a silicon alloy steel, which, thanks to the presence of silicon in the steel, it forms a thin layer of silicon oxide on the surface of the steel when exposed to liquid lead. And that silicon oxide, better known as quartz, is very corrosion tolerant. It actually works very well. So the Russians are going to use this steel now to build their first commercial lead-cooled reactor in the Tomsk region in Russia, and they are going to take it in operation in 2027. Now that steel has a problem. It becomes brittle under irradiation. Means it becomes like glass. Well, not while it's in the reactor, but after you take it out at low temperature. So if you, by an incident, would drop a fuel assembly, then it might break, and that would be a bad problem. So we realized that this was not the perfect solution, and therefore in 2008 I asked one of my colleagues at KTH, who was working on corrosion science, if he had an idea how to solve this, and thought that yes, we had an idea, and then that was then the basis of the innovations that later become our company. It was to use aluminium as an alloying element in the steel. And aluminum alloyed steels were invented in Sweden 100 years ago, and they are used for heating wires like the ones you have in your toaster at home.
Okay.
So this is not a very advanced steel. It's rather actually simple to make, but it was not suitable for using in a nuclear reactor. So we had to modify this toaster steel into something we had less chromium and that had few magical elements included. So we added the right portions of zirconium, titanium, and niobium into the steel. And I should say my colleague, because he's a steel magician. And like magic, it became totally corrosion tolerant in liquid lead. And we have tried it for 2 years of exposure at operating temperature, comes out of the experiment mirror shiny. And we have tried it at 800 degrees C accident temperature, and it also maintains the integrity of the protective surface. So this is our innovation, and we've been working together with the Swedish established steel industry. Former Sandvik, now Aleva, has been instrumental in industrializing this technology. It has taken time, clearly. We started 2008, but now, 16 years later, we actually have a material that can be industrialized.
But good things take time, right? That's nothing goes ever easy. Yeah. On the topic of the coating, so we talked about quartz being formed in the silicon alloy. What is formed in the aluminium alloy?
Yeah, so the neat thing is that the aluminum alloy steel, it forms aluminum oxide on the surface, which is a very thin protective layer of sapphire.
Isn't that beautiful? Yeah, so we've got a sapphire that protects us all from the risk of meltdown.
Yes.
So talking about meltdown, and we've covered safety, but I think it's such an important, critical element. We're going to talk about it one more time. Chernobyl, Fukushima, 3 Mile Island. Yeah, how do you reflect on those awful events that happened? Yeah. And how do we talk about this reactor design addressing issues like meltdown, waste, and public perception? So we've talked about the science. How do you shift the discussion around these points?
And so what we are addressing with this technology are major flaws that's led to these accidents. We have a coolant medium that will not disappear by boiling. We have a coolant medium that, if in case there still would be a coolant, that will protect you from the radiation, because liquid fed is the definition of gamma shielding. We have one thing which happened in Fukushima was that the emergency diesel generators that were supposed to circulate the emergency cooling water were destroyed by the tsunami. So we have addressed that, because liquid lead is able to circulate by itself naturally with a better performance than most other coolant media. And so the liquid lead performs a number of functions that allows you to manage accidents without the intervention of human operators.
So you're studying the disasters, and you've reverse engineered solutions to each of the things that cause critical issues.
Indeed, that's a good way of playing it.
And if we think about the unique characteristics of lead that might make it, might introduce new factors. Have you thought about those factors?
Indeed, of course, there's no free lunch. Liquid lead is opaque; you cannot see through it, which means we have to inspect our fuel assemblies during operation with other means than visual means. That is a challenge. So, need to refine existing methods for that, like ultrasonic inspection and other ways of inspecting this. This is one remaining challenge. Another challenge is that the lead actually freezes at 327 degrees C. So we will not have any overheating accidents. We will have overcooling accidents where the lead freezes.
And you lose power.
Then the system will. If you do that in the same time, of course, yes. Then you need to make sure that lead freezing does not lead to that the fuel rods are damaged, or that your steam engine or your tubes are damaged. So this is one thing that we are going to investigate in the near future in our experimental facilities.
So let's pivot to the conversation around renewables. In Australia in particular, but globally as well, the renewables industry is advocating a lot for renewables plus storage. There's interesting data around the cost of storage dropping really dramatically. Where's nuclear fit into the mix, and how does it complement or compete with renewables plus storage?
Well, that's a very interesting story, of course, and the challenge. So far, indeed, the nuke at this moment, and still yet, not existing nuclear and new nuclear is cheaper than renewable plus storage. There have been a number of studies on the cost of producing power in a national energy system. Where crazy in Sweden, we are really we are in a good situation because we can store energy in the hydropower stations. So our hydropower stations are used to actually store energy, which today is makes it possible to balance out intermittency of free power in the country. And when you then study a transition going from the current system with balancing hydropower, nuclear, and wind to a system with only hydropower and wind, then you see that at a certain fraction of wind power, then the prices skyrocket. So those studies have indicated that the ideal fraction of nuclear power in a system which includes renewables is about 20 to 30%.
So you need a baseload power source.
We need it. Even if you have cheap storage, you still need about 20. The most cost efficient solution is the system with 20 to 30% nuclear power baseload.
It's interesting. I've read recently in the press that the Netherlands experienced its darkest couple of weeks in a long time, and that means reduced wind and reduced energy from solar power.
Yeah.
These are the sorts of events maybe that we haven't been thinking about, and where baseload becomes really important, I imagine.
Yeah, I mean, where we had a few days before Christmas in Scandinavia, where electricity prices were up by an order of magnitude, by more than 10 times, because of there was basically no wind in Europe during those days, and we had become really too reliant on the supply of power from other countries. So what we are seeing right now in some countries, especially in Germany, but also recently in Scandinavia, Netherlands, an example, we are seeing issues related to having a too high fraction of intermittent power sources on our power grids.
All right, let's go now to business and unit economics and maybe the competitive landscape. So we know that scaling isn't just about technology, it's about making things financially viable in a business context and scalable. First question, when we caught up a couple of days ago, we talked about two figures. So $500 million to get to first criticality and your factory, and then a long-term target of 6 cents a kilowatt hour over 25 years. So those are pretty ambitious, given the context of, what we're talking about in the context of nuclear power.
Yeah.
How do you expect to drive those efficiencies? One, on getting to criticality of manufacturing. Two, how do you get to that 6 cents per kilowatt hour?
Yes. Now, the first part of the question is by being very diligent and having a very efficient process going towards your first demonstration unit, to show that really we can produce nuclear power in an innovative facility. So, and our way of approaching that is to attract the best engineers and the smartest people. I think we are under transformation from where the SMR developers have been able to attract quite a lot of venture capital, and that was time to deliver. And then some of the competition will not survive this.
So we usually talk about economies of scale in the context of nuclear, particularly in some of the larger reactors that were developed early. You get to a certain scale, you spend a bunch of cash, and then you get cheap power. You've talked about in our conversations economies of multiples. Can you unpack what that means, what it means for your reactors, and why it's game changing in an SMR context?
Yes. Now, economy of scale works because if you have a nuclear reactor, it doesn't matter what the power is. You need to have the same amount of staff anyway. You need the same amount of security staff. You need the same amount of operators, which means that a 1,000 megawatt reactor has about the same staff as a 100 megawatt reactor. Right. So economy of scale is there. Now, that worked in the 80s in Europe and in the 90s in Japan because you built large reactors all the time continuously. So you never lost competence. So you actually were able to learn from your mistakes. And eventually, large reactors were built in Japan in 3.5 years, which, if that worked now, could mean that nuclear power would be totally competitive. Now we've lost that competence because we do no longer build many large reactors in series. China possibly does it, but nowhere else. So now we have really bad examples of large new builds: Finland, France, the UK, the US, where it has taken 15 to 20 years to build. It's cost. Yes, Brian, and that immediately translates into interest rates. That's skyrocketed. What we need to, so economy of scale doesn't work in the West any longer because we don't build huge series of large reactors. Now, instead, what we can do then is to apply the principle of economy multiples, like the wind power industry. I mean, it's interesting to see they have actually very successfully found an optimum size of their plants, which is between around 3 megawatts per unit, where they can build large series and deploy them, and it's very cheap to do that. There are wind power units plants that have been designed for 10 or 15 megawatts. Nobody builds them because there is no economy of multiples there to be found.
Got
it. So we need to find that sweet spot. We don't know where it is. We believe that maybe 55 megawatt electric might be there. Some of our competition thinks that 300 megawatts that might be the sweet spot.
So for context of the audience, 1 megawatt equals what in terms of power?
It's feeds enough to give power to 1,000 households.
Great. So 5 megawatts, 5,000 households. Yes. 300 megawatts, 300,000 households. Got it.
Yep. So that's why, I mean, if you get one big nuclear power reactor today can supply power to a city of Stockholm, 1.5 million people. We are not aiming for you.
5 years to get to criticality by 2029. 2 years to build a factory.
Well, yeah, I mean, okay, so indeed, so our first demo units will be taken into commercial operation in 2030. That's our plan. And then that unit will, because this is handmade, this is not made in a factory.
Handmade, yeah.
Yeah. This, we will use it to produce high quality heat, which, for instance, for process industry. And that is better paid than electricity today in most European countries. So that is the way we can actually get economy into the first unit, even though it's not serially produced. But then by then we will have shown that the technology works. We believe that then we can attract customers that are willing to place orders of 10, 20 units. And once you have those orders, then yes, you can build a factory. To build a factory maybe takes it's 3 years from start of project to when you actually are in production. But then the idea is that in this factory, yes, then we produce every month after ramp up a unit per month.
So you've got simultaneous production of units.
Yeah.
The build time is 8-12 months from start is what you're targeting. What validation have you done of those timelines? How are you? So those are your targets. How have you validated that it's possible?
Historical data showed that in the 60s, when you actually built small reactors.
For nuclear submarines?
Yeah, for nuclear submarines, but also commercially. So the first commercial nuclear power plants in the United States, for instance, were 60 megawatt electric, exactly like our size. And in particular is a very successful example of General Electric's reactor in Bauxito, which was built in 18 months, 1.5 years.
Wow, okay.
So there is precedence. This can be done. Of course, regulation was different, but now we will be many units. So to get the permit for the first unit will take longer time, but then once we have that permit, then you can, there is precedence. You can build a nuclear reactor of this size in 18 months.
Okay. That's fascinating. Yeah. Elon Musk famously said he would build lots of electric cars very quickly, and it took him longer than expected. Yes. What scaling issues do you anticipate in building out of your first factory?
This is a very important question. Remember, we have seen examples, in particular here in Sweden, where the new battery manufacturer Northvolt scaled up too quickly their factories and got into troubles because of trying to scale up too quickly. So we need to understand the experience from similar projects like Tesla or like Northvolt to see why was the whole process of building the Tesla factories delayed? What did they learn? I mean, eventually they are now in production, and they work very well, right? So we need to analyze the experience from similar projects in detail and understand what is the factors behind success.
Got it. And failure.
Yeah.
Let's talk about the competitive landscape. So you got, SMRs are the flavor of the day. In the last 6 months, you've had Google and Amazon both come out with big deals, investing in SMRs. How does Blykalla differentiate itself in this increasingly competitive market?
Yes, okay. It's a good question. Because we use liquid lead as a coolant, we produce steam at 530 degrees Celsius, which some of the competition is not capable of doing. So which means we are ideally suited for certain process industries, like production of biofuel. Here we are beating the competition simply because we have the right temperature of our steam. And that's it. But that's very important on certain markets where you want to switch from fossil fuel for transportation to biofuel. So this is where we do have a competitive edge and a unique selling point.
Could that heat be used for steel manufacturing, so?
Absolutely. And particularly here also in order for steam manufacturing to go fossil free, they need to replace fossil carbon in their process with biogenic carbon. So with our reactor, we can produce biocarbon or biochar, as it's better name, that the steel industry can apply to go fossil free.
Interesting. So there's a big industrial focus in the way that you're thinking about the applications of biotechnology.
Yes, indeed. So this will be our first commercial application. So this will be things you can produce with high quality heat. Like hydrogen can be made 25% more cheaply if one uses high temperature electrolysis as compared to conventional electrolysis. Then once we are right now, when we don't have a factory, we are not able to compete on the electricity market in Scandinavia, but here on Svalbard we will be. But once we are in serial production there, then we can be competitive on that market as well.
And tell you that 6 cent.
Exactly. Now, if our first unit, which is handmade, we'd be producing electricity at more than twice that cost. More than 12 cents per kilowatt. So it's not competitive on most markets. But yeah.
So a final question in the commercialization discussion. You've talked about the partnership with, is it KBB? ABB.
Yeah.
So the partnership with ABB, there's a partnership you've signed with the Swedish government. What role do these, so we've talked about utilities as potential purchasers. We've got Google and Amazon coming in as purchasers. We've got ABB coming in as a scaling partner. What role do these various partners play, and how important is each style of partnership with the way that you approach this?
Yeah, so indeed, in order to translate our technology, our innovation, our technology into industrial product, we need partners with industrial, let's say, skills and experiences, right? We are partners in let's say the supply chain. That's very important for suppliers of uranium, suppliers of certain steel manufacturing technologies. Absolutely. These are essential. We need to have off-takers, of course, also. Companies that produce, that's actually use hydrogen. Companies that will use biofuels. Such partnerships will be crucial, and we expect them to. Let's say we are working on those partnerships. And we believe we will have a new place over the next year.
Wow. Right.
Yeah, and then of course we have this long-standing partnership with Uniper, which we haven't touched upon yet. So Uniper is the owner of the largest nuclear power plant in Sweden, and we have a collaboration agreement with them, And then but currently so they would be a natural customer for us, of course. Now, currently they are owned by the German government, so the German government is not planning to build any new nuclear units, which is okay, their decision. But the European Union has also requested that Uniper, the German government must sell Uniper to the market, and no later than in 2028. And once Uniper is in private hands again, or owned by somebody else than the German government, then we have that. Then this will become a very important partnership.
Yeah, I guess that's the opportunity that the way that I see this is the opportunity that your technology and your approach specifically presents is the capacity to pump out these things like you pump out cars and, pop them in places. What strikes me as interesting from our conversation is that your company, the way you built your company, you're very efficient at constructing things, based on your personnel footprint. I wonder if then you will also be quite good at operating things, because presumably these small modular reactors are going to be simpler to operate. You've got to be designing that downstream. Yes. So is there a world where you don't have to develop a much of a domestic nuclear capability subject to, the relevant supply chain, value chain issues, safety issues, regulatory issues, then actually you act as an operator of these plants? I come from a software as a service background where we deliver service, right? So is there, and first of a kind technology is looking at this as a service deployment model very broadly. Do you become a global power utility as opposed to a manufacturer of stuff that you ship? I think that's where I see what's really interesting in the direction.
Yeah, that is true. So operations as a service, nuclear operations as a service. This is an interesting business area. And we ourselves in Blykalla, we are not seeing ourselves as in that field, but there are other companies that are really doing this. So that's currently our operating reactors for in the Nordic countries, and that look seriously into this. So I think there will be companies offering operations of nuclear power plants as a service.
So I guess there's an emerging ecosystem of this happening at scale. Yes. Brilliant. Faso. All right, so let's move to close. So every founder faces challenges, and I'm sure you've faced yours. What's been the toughest moment so far, and how did you overcome it?
Yeah, there is a particular event that happened. We were looking for investors. We were still basically a basement company then. We were contacted or came in contact with an investment company in Dubai. And they said that they wanted to go invest in high-tech European companies. And that they were very supportive. I mean, we were to support you with all the funding that you need, so that you can focus on the technology. And in the end, after a few months of negotiations, after they had visited Stockholm and seen our laboratories, they agreed to sign an investment agreement of $200 million. And this became global news. It was in the Forbes magazine. So for a while, we felt very happy and started employing people. I started employing my best PhD students in the company, and we attracted confidence from other countries to start working with us. And then unfortunately, it turned out that this was a scam. This was an unserious investor, that they didn't have the funds that they claimed they were going to invest into our company, but they were actually using this investment agreement as a means of trying to attract the secondary investments into their fund. And that was a very difficult time. It almost killed me. Had to fire my best students and friends, and basically put the company into hibernation. And it was a very difficult thing.
How did you cope?
I went to Svalbard.
For the first time?
That was actually, for the second time I came to Svalbard was when this happened. And then I was really fortunate to have a good good partner, my girlfriend, who understood that I needed to relax. And but then I went back to university. I had stopped taking students. I was able to actually do science. So I thought, okay, I will be maybe doing this for a while. But then an opportunity appeared to actually apply for funding from the UK government to design a small modular reactor, an SMR, for the UK power grid, because the Britain thought they needed to create a platform for building near nuclear in the UK. And then we were able to come back into commercial development.
And in contrast to that, which sounds like it's a really interesting and creative period where you sort of you get to know yourself and understand how your resilience plays through in real life. What's been the proudest moment? Something that made you feel, this is why I pursued this path.
One of the proudest moments was when I went into our nuclear field lab. I was going to assist my colleague. I'm normally not studied into the lab because I tend to break things. But this was a special experiment. We were, for the first time, going to try to make a fuel type, which is known as uranium nitrate, by a novel process. We were going to make this by exposing uranium hexafluoride to ammonia gas. And we went into the lab, we started the process, and he started heating up the equipment, furnace tube, and nothing happened for a while, but then the process started, and out of the tube came a fine green snow pouring out into the quartz tube that we had. That's very moment I felt, wow, an idea has become reality, and I was able to be there at that moment.
Let's zoom out to the broader picture, which are the opportunities ahead in climate and the future of nuclear energy. So one question that I ask every guest, we always talk about opportunity. What's one big opportunity in energy or in the climate space that you think is not getting enough attention outside of the one that we'll be talking about?
There are things that there is storage of energy in compressed air. Personally, I'm quite fascinated by this thing.
Why specifically compressed air?
It's very simple, and I mean it can be done everywhere, and the question is scalability. But then again, you can do it in terms of multiples instead of scale of the facility, possibly. So this is something I would personally would have a look into if I was in energy storage.
Got it.
Maybe I don't know enough, and then maybe there are showstoppers that is stopping this technology from being commercially successful. But this is about what I would look into.
Yeah, it's interesting. Yeah, sometimes the obvious things are the ones that most people overlook. So that's it. That's an interesting perspective.
When it comes to nuclear technology, okay. If fusion is ever going to work, it needs to be the proton-boron cycle. So I would put if I would be an evaluator of, let's say, of somebody funding a fusion project, I would advise them to look into the proton-boron cycle.
Why?
Because both proton and boron exists on the planet, whereas fusion does not.
Brilliant. Okay, so rely on something where we actually have the stuff to make it work. Yes. As opposed to magic in the process. I like it. Everything with you, Janne, I've started to realize is everything simple. Keep it simple, keep it foundational, get the job done.
Yes.
All right, so fast forward to 2030. Where is Blykalla and where is the small modular reactor industry?
By 2035, we will have commissioned our factory for producing reactors, the first one. Sweden, we will have experience from having operated our first demo units, a couple of years experience. We will hopefully we will be one of the 5 major SMR vendors in terms of order books. And most importantly, we will be able, of course, to have addressed we have started to address the energy, the climate issue, and the security of supply issue. Yes.
And where is SMRs? What are they? Are they replacing nuclear? Are they replacing all baseload power?
Depends on where you are. I mean, in Sweden, they would be replacing. They would be able to extend the need of the production of baseload, so it would come on top of the existing nuclear power fleet. The units that are still operational in Sweden will be so for another 30 years. We would not replace. We would we would increase the size of the nuclear power fleet.
I guess mass electrification means we need more power. So this comes in addition.
Exactly. This would we would use the power we produce to enable the transition to a fossil-free industry.
A very final question. Who's your biggest inspiration?
Inspiration? There are several. I mean, in science, it's Enrico Fermi, the person who built the first nuclear reactor outside of Chicago in 1942. He is a great inspiration both in terms of his ambitions, his goals, and the way he conducted science. Really. And then privately by my uncle, I was a scientist. But I visited his lab. As a kid, I thought, yes, I also want to be a scientist. And then, industrially, speaking, irrespective of the way Mr. Musk behaves, when he tries to be part of political discussions, I think his way of changing the way you deploy renewable technologies rapidly and relentlessly and very efficiently is a source of inspiration. Yes.
Is relentless is the absolute word for Mr. Musk.
Yes.
All right, yeah, thank you very much. It's been an absolute pleasure.
Thank you, Anton. Great.